Hi everyone. First of all, I wish all of you and your families are healthy and safe. Second, let me remind you that the exercise for Unit 2 is due next Monday, the 20th of April. Okay, so please read the problem. If you have not read it yet, you can find it on the virtual campus and send me an email if you have any question about what you are supposed to upload to the task. Okay? And today's lecture is going to focus on different types of graphs, different families, examples of graphs that are special for some property or that we are going to use in our study of different methods and algorithms. Okay, so they are going to be examples that are important for some reason that we are going to use in future lectures. Okay, and you need to know their definition and their properties. Okay, so the first type of graph that we are going to study today is what we call complete graphs. So this is a family of non-directed graphs in which each vertex is connected to any other vertex. Okay, and remember that since this is a non-directed graph, the direction is the connection is in both directions. Okay, so for instance, the easiest example of this kind of graph is a graph with just one vertex. Okay, so a graph with just one vertex is a complete graph because every vertex is connected to the other vertices. Remember that in non-directed graphs we do not have loops, and since there is only one vertex, then the requirement is fulfilled. The next graph is going to be the graph with two vertices that are connected to each other. Okay, so usually we give the name k sub n, where n is the number of vertices to this type of graphs. So the first one is going to be k1 and the second one is going to be k2. Okay, the third graph in this family is the complete graph with three vertices, which is k3. Okay, and notice that when I say kn, there is only one graph with that number of vertices that is complete. If I know the number of vertices of a complete graph, I know everything that I need to know in order to define the graph, because I know the number of vertices and I know that all the vertices are connected to the other ones. Okay, so mathematically we say that any two complete graphs with the same number of vertices are isomorphic. Okay, so in the next slide, I will return to the theorem in this slide afterwards, but in the next slide you can see pictures of K4, K5, K6, and well, it's not difficult to draw pictures of other complete graphs. You just draw the number of vertices and then you connect each vertex to the others. Okay, so in this study of the families of graphs, we also want to know or to study the different properties of the elements in the graph. Okay, so the number of vertices, the number of edges, the degrees of the vertices, and so on. Okay, so for instance, in complete graphs, we of course have that trivially kn has n vertices. Okay, that is by the very definition of kn, it's a complete graph with n vertices. The theorem here in the slide gives us the number of edges in the complete graph of n vertices, and this is given by n times n minus 1 divided by 2. This is also what we call the combinatorial number n over 2. Okay, so combinatorics is another part of discrete mathematics that, as I've already told you, we unfortunately don't have time to cover, but it's also important regarding the complexity of some algorithms and of some data structures. Okay, well, but in any case, the number of edges in a complete graph with n vertices is given by n times n minus 1 divided by 2. Why? Because each vertex is connected to the others. Okay, so for each vertex we have n minus 1 vertices that are incident in it. Okay, so there are n minus 1 edges incident in each vertex. If we multiply by the number of vertices, we have n times n minus 1. But we are counting each edge twice because it is incident in two different vertices. So the total amount is n times n minus 1, but divided by 2. Okay, and you can check that in fact this gives the correct number of edges in the examples here in the slide. For instance, if I take n to be 1, the number of edges is 0. If I take n to be 2, then n minus 1 is 1, and 2 divided by 2 is 1, which is the number of vertices that K2 has, and so on. You can check that this formula gives the correct number of vertices of edges in the complete graph of n vertices. Okay. Another thing that is interesting to know about a graph is the degree of the vertices. Okay, and in this case, it is clear that the degree of any vertex is n minus 1 because it is connected to the other vertices in the graph. Okay, and again, you can check that in the examples in this slide and in the examples in the next slide. You always have n minus 1 as the degree of any of the vertices. Okay, so this is a very simple example, but it's important. For instance, we will study the graphs K4, K5 as examples of what we call planar and non-planar graphs. Okay, something that we will return to in a future lecture. Okay, so this is about complete graphs in the case in which we have no direction in the edges. But we can study a similar notion when we have directed graphs, when we have a direction in the connection. Okay, in this case, what we call a complete directed graph or a tournament, I will explain the name tournament in a minute, is a directed version of a complete non-directed graph. Okay, so let me explain what I mean by that. We take a complete graph. For instance, imagine that I consider a very simple graph, like for instance K3. So I consider an undirected complete graph like this one, K3, and then I give direction to the edges in the graph. Okay, and what I get is a complete directed graph or a tournament. Okay, notice that I can do that in different ways. When I have complete non-directed graphs, then there is only one complete graph for each number of vertices, and we call that K sub n. Okay, but when we have, for instance, 3 vertices in a graph, and it is a complete directed graph, we can have different non-isomorphic graphs that are have not the same connections. Okay, so for instance, imagine that instead of doing the assignment of connections as in this graph here, I'm going to do it in this other way. I form a cycle. Okay, so these two graphs, this one here and this one here, are both tournaments or complete directed graphs of three vertices, but they are not equivalent, they are not the same, they are not isomorphic, because in this case here I have that all the vertices are reachable from the others, while in this case here notice that this vertex is not reachable from the other vertices. Okay, so these are not the same graph, but both of them are complete graphs with three vertices, directed complete graphs with three vertices. So this is the first difference with the complete graphs in the non-directed case. Here we can have more than one directed complete graph for a given number of vertices. Okay, so this is something that is different from the previous case. Okay, so let's return to the name tournament. Why do we call these graphs, this kind of graphs, tournaments? Well, they are called tournaments because they can be seen as a representation of the different matches that we can have in a sports tournament. Imagine, for instance, that we have the Football World Cup or something like that, and we have several different teams that have to play a match against the others. Okay, so in that case we can represent each of the teams as a vertex in the graph, and then we can represent the different matches as directed edges. For instance, we can establish the direction depending on what is the team that is local and what is the team that is a visitor. Okay, so when we have this kind of tournaments in which each team or each player, each person that takes part in the tournament plays against the other participants in the tournament, we can represent that with this kind of graph. Okay, so that's why we call these graphs tournaments. Also, a very important property that we will study in a future lecture, maybe this very same week, is that these tournaments always have a type of path that is very important, that is what we call a Hamiltonian path. A Hamiltonian path, as we will study later, is a path that visits all the vertices in the graph without repetition. Okay, so for instance, in this tournament here of 6 vertices, we have this path 1, then 2, then 4, then 6, then 3, then 5, which visits all the vertices without repeating any of the vertices in the graph. Okay, this is what we call a Hamiltonian path, and we will show that tournaments always have a Hamiltonian path of this type. Okay, a path of this type. And this is a very important property because not all types of graphs have this kind of path, and in fact in practice it's difficult to know whether a graph has a Hamiltonian path or not. Okay, so we will return to this kind of problem, finding a Hamiltonian path in a graph later on our lectures in this unit. Okay. Also, this kind of graph can be used to represent some games that I'm sure you know. For instance, the famous rock, paper, scissors game can be represented as a tournament, and also its more fun variant as seen in the Big Bang Theory, which is called scissors, Spock, paper, lizard, and rock. Okay, so here you can see a representation of this game as a tournament in which we have as elements the different choices in the game, and as edges who wins against what. Okay, So this is also a tournament, and this can be also generalized, has been generalized to more complicated games in which you have, of course, rock, paper, scissors, and many more elements, in this case 15 elements. And as you can see here, this is also a tournament. Okay, so as a funny fact, you can see that this kind of game is also a tournament. Okay, so let's move to the next family of graphs, which is what we call bipartite graphs. Okay, so let's first see an example of a bipartite graph, and then we will return to the definition. Okay, so the idea is that this graph here is bipartite because we can divide it into two different parts, U and V. And these two parts can share edges from one to the other, but have no edges inside the parts. Okay, so when we have the elements in U, you can see here that there are no edges connecting two vertices in the same part, no edges connecting vertices in U, no edges connecting vertices in V. Okay, so this is the general definition of a bipartite graph. Okay, we say that a non-directed graph is bipartite if we can divide the graph into two different parts, okay, U and V, in such a way that there is no vertex, no edge connecting vertices which are together in U, and no edges connecting vertices that are together in V. We can have vertices from U to B, edges from U to B, but we cannot have edges inside U or inside B. Okay? And let me give you an example to see that in general we can have more than one way to divide vertices in a graph to make it bipartite. So for instance, imagine that we have a graph like this one with connections from vertices in one part to the other, something like this, for instance. Okay, of course here I can take this part to be U, and I can take this part to be V. Okay, and this makes the graph bipartite because there are no connections, as you can see, among the vertices in U, and there are no connections among the vertices in V. But I can also make a different division here, for instance, taking these vertices as U and these vertices as V. Okay? In this case, as you can see, again, there are no connections among the vertices in U, there are no connections among the vertices in V. Okay, so for a graph to be bipartite, we don't need to have a unique way of dividing the vertices into sets U and V, but we must have at least one way of dividing the vertices into the two parts U and V. Okay, and in that case we say that the graph is bipartite. Okay, so it may seem that it is difficult in general to see whether a graph is bipartite or not, because we might have to check all the different ways of dividing the vertices in the graph into two different parts, and that can be hard. There are many different ways to divide the vertices of a graph into two different parts, and we could have to check each different possibility. But this theorem here gives us a way of checking whether a graph is bipartite or not, without having to resort to enumerating all the different ways in which we can divide the set of vertices into two different parts. And namely, this theorem says that a graph is bipartite if it does not contain cycles of odd length. Okay, remember that the length of a cycle is the number of edges in the cycle. A cycle is a path that starts and ends in the same vertex. And the idea here is that, of course, if we have two different parts and we have no connections among the different parts, among the vertices in U or among the vertices in V, if we want to go from a vertex to itself using some edges in the graph, if we want to form a cycle, then we always have to go back and forth between U and V. When I'm in U, I need to use an edge to go to V. And to return to U to close the cycle, I need to use another edge to go to U. I cannot go inside V because there are no connections there. Okay, so whenever I have a cycle, this cycle must have a length which is an even number, because I have to go to B and back, go to B and back, go to B and back. I cannot connect vertices inside U and V. That is the idea of the proof of why this theorem gives us a condition which is sufficient and necessary for a graph to be bipartite. Okay, and this allows us to check cases in which a graph is bipartite is not so clear. Okay, so for instance, consider this graph here. Okay, so it may seem at first glance that this graph is not bipartite, but this graph is bipartite. If I take, for instance, this set of vertices as U, and this set of vertices here, let me have to connect these two vertices, so this one with this one, these two vertices here as V. Okay, notice that there are no connections between this vertex that I'm going to call 1 and 2, which are in V, and there are no connections between this vertex 3 and 4, which are in U. Okay, so this is the very definition of a bipartite graph, and although it may not seem evident from the original way in which I draw the graph, this is of course a bipartite graph. I could have done something different. I could have drawn the graph like this: 1 and 2 on one side, 3 and 4 on the other side, and then I connect 1, 2, 3 and 4 and 2 to 3 and 4, and then it's more clear that it is bipartite. But it's exactly the same graph. Remember that in a graph, the only thing that is important is what is connected to what. Okay, so if I don't see this from the way in which the graph has been drawn, in which the graph has been represented in a picture, I can use the theorem that we have just seen. I can try to find odd length cycles in the graph, and here the only cycles that I can form are the ones that use all the edges in the graph. If I start in 1, I can go to 4, then to 2, then to 3, and go back to 1, and that has length 4. Okay, and if I want to form another cycle, for instance, I can go from 1 to 3 and back, and that has length 2. Okay, so any cycle that I can form here has length which is even. Okay, so I can check that. Imagine that I have a much more bigger graph with many thousands of vertices or millions of vertices, how can I do that? I can check whether it is bipartite, not by trying all the different possibilities of dividing the graph into two parts, which would be extremely high, but computing the number, the different reachability matrices. Okay, remember that the reachability matrices gives us the number, whether there are paths of a certain length. Okay, so for instance, the first matrix is the zero reachability matrix, which is the identity, which gives us cycles of length 0. The second one is the adjacency matrix, or also the order 1 reachability matrix, which gives us paths of length 1. Okay, and if I check in the main diagonal of the matrix, I have the cycles. Okay, so in general, in the k order reachability matrix, I have paths of length k where there are ones in the matrix, and if I check the main diagonal of the matrix, I can see whether there are cycles of that length or no. So I can compute all the different k reachability matrices and check if in the main diagonals of the odd order reachability matrices there are cycles or not, and with that I can see whether the graph is bipartite or not. I don't need to compute all the different ways in which I can divide the set of vertices, which would be much more than the number of computations that I need to do in order to find the reachability matrices. Okay, so I told you that I wanted also to study the different properties of these graphs. So what is the number of edges, what is the degree of the edges, what is the number of vertices, and so on. Okay, so in the case of tournaments, I have not covered that. That is an exercise for you. Okay, you need to try to find what is the number of edges, what is the number of vertices, and what are the degrees of the vertices. Okay, it's very similar to what we did with the complete graphs in the non-directed case, but here be careful with the degrees. Okay, it's very similar, but the degrees are a bit different. I will also upload a short video covering the case of the tournaments, but please try to think it on your own and then check if you have got it right. Okay, what are the number of edges and degrees in the case of a bipartite graph? Well, it depends. Okay, it depends on how many connections we have. Okay, but notice that if we have m vertices, oh sorry, not so easy to write on this program. So m vertices on the u part and n vertices on the v part. Of course, the total is m plus n. Okay, and then the maximum number of edges is m times n. Okay, and this number of edges is reached, well, m times m is reached when we have all the different possibilities to connect the vertices from one part to the other. Okay, so for instance, imagine that we have 2 vertices here and 3 vertices on the other part. I can connect this vertex to the other 3, and I connect this vertex to the other 3. Okay, and in that case I have exactly m times n edges. Okay, so the number of edges is at most m times n, that is the maximum. Okay, and the degrees are, for this case, for the case in which I have m vertices, at most n, and for this case at most n. Okay, in the case in which they are connected to all the other vertices in the other part. Okay, and this takes us to the next case of the graphs that we are studying in this part of the unit, which is what we call complete bipartite graphs, which are graphs that are at the same time complete and bipartite. But if they are complete, then they cannot be in general divided into two parts which are non-connected among themselves, which have no connections between the vertices which are in the same part. So we first impose the condition that the graph is bipartite, as for instance in this situation here, we have two different parts, and then when we have those two different parts, u and v, and we impose that the vertices in u are not connected between them, the vertices in v are not connected one to each other, then we impose, after that, we impose that the graph is complete in the sense that it has as many connections as possible, and then it means that each vertex in u is connected to each vertex in v, and since this graph is non-directed, then all vertices in v are also connected to all vertices in u. Okay, and in this case, obviously, if I know the number of vertices in one part and the number of vertices in the other part, there is only one complete bipartite graph. If I know the number of vertices in each of the parts, then I know all that I need to know about the graph. I know the total number of vertices, which is of course m plus n, and I know all the connections. All the vertices in u are connected to all the vertices in v. This gives us, as we have reasoned before, m times n edges, and all the vertices in the part with m vertices have degree n, and all the vertices in the part with n vertices have degree m, because they are connected to the m vertices in the other part. Okay, so this is exactly the limit case in that we mentioned in the previous slide. Okay, since all that we need to know are the number of vertices and the number of on one part and the number of vertices on the other, in order to define the graph, we give these graphs the name k sub nm. Okay, so they are complete bipartite graphs with n vertices in one part, m vertices on the other. So for instance, let me give you we can have K34, which has 3 vertices in one part, 4 vertices on the other part, and all the vertices are connected to the vertices in the other part. Okay, so this would be K34, and this is the only complete bipartite graph with 3 vertices in one part and 4 vertices in the other. There are no other possibilities. Okay, so these graphs are important, as we will see, in connection to problems also of planarity and to some games that we will mention, similar to the Königsberg bridge problem. Okay, so please remember this definition of complete bipartite graphs, because it will appear again in future lectures. Okay, so let me go to a different family of graphs, which is also important, but it's very simple to define. These are what we call the path graphs and the cycle graphs. Okay, and as the names imply, these are graphs in which we have either a path or a cycle. Okay, so the path graphs are going to be denote by p sub the number of vertices, and the cycle graphs are going to be denoted by c sub the number of vertices. Okay, so for instance, let me give you some examples. We go back to the ones in the slide, and if we have p3, we have, for instance, this picture here, in which we have 3 vertices and they form a path. And if we have C4, for instance, we have this graph here, in which we have 4 vertices forming a cycle of length 4. Okay? Notice that these names sometimes are not unique. What do I mean? That for instance, in this case here, C4 is also equal to K22. Okay, remember that I can also draw this graph if I change the position of the vertices in this way. Remember that this is the example that we used in order to show that this graph here is indeed bipartite. Okay, when we studied a few slides back the concept of bipartite graphs. Okay, and also notice that, for instance, if I take this graph here, this graph is both C3 and also K3. Is the complete graph of 3 vertices, but it's also C3. It's a cycle of length 3. And for instance, P2 is also K2.